This one's for Evo. I know you're still working on the chemistry of life, and you have some questions that you had proposed to Sky Scholar, which is Pierre Marie Robitaille, concerning chemistry. I want to direct you to paper number 357 on the Vixra. On my article, or on my page at least, where it says I'm the author. The Haber process. Naturally occurring Haber process during stellar metamorphosis, or how to find water worlds in exoplanet data. How to find water worlds and what the Haber process is. Hi, Celeste. Really excited. She'll be here in just a few days. This paper was written July 22nd, 2018. I don't know if you saw that, Evo. Baz, this is pretty cool too. Maybe one day we might make a little video outlining this, because we have a useful graph here. Of course, I stole this graph. I don't know where. I think I should have given them credit. Anyways, ammonia is found in late-stage stars such as Neptune and Uranus. It is also present in intermediate-age stars such as Jupiter and Saturn. Given the sheer amount of hydrogen and nitrogen available to chemically combine into ammonia, it is clear that production of ammonia is a natural process in stellar evolution, and we can mimic this with the Haber process. A naturally occurring Haber process runs counter to the establishment's false worldview that stars cannot cool down enough to form huge amounts of organic and non-organic molecules. We know it happens because we have direct and indirect observational evidence of it happening. Let's do a little refresher here. Mainstream astronomers don't realize planets are older stars, meaning the process of planet formation is the process of stellar evolution. The nitrogen and hydrogen required to make ammonia is present in the star itself, because that's what the star does. It takes that nitrogen and combines it with hydrogen. There's one nitrogen, and then there's three hydrogens surrounding that nitrogen. That's ammonia. There's a lot of hydrogen and nitrogen inside of young stars, and of course, as they evolve, they're going to be producing a hell of a lot of ammonia. So here we go. I'll go ahead and outline this out to you guys. The Haber process is the combining of nitrogen gas with hydrogen gas to make ammonia under high temperatures and pressures. The process takes around 200 times normal atmospheric pressure and about 450 degrees Celsius, with hot iron beds as catalysts. The process below is outlined as such. It says here, number one. Let's see, number one, right up here. Ooh, look, it's on the other page so you can see it as I read. Number one, having obtained the hydrogen and nitrogen gases from natural gas in the air, respectively, they are pumped into the compressor through pipes. And that's right here, pumped into the compressor. Right there. The gases are pressurized to around 200 atmospheres of pressure inside the compressor. So lots of pressure in that compressor. Pressure compressor. The pressurized gases are pumped into a tank containing beds of iron catalyst at around 450 degrees Celsius. In these conditions, some of the hydrogen and nitrogen will react to form ammonia. So here's the iron bed catalysts. They're really, really hot, 450 degrees Celsius. They go in there and they produce the nitrogen plus the hydrogen, making ammonia. And there's the cooling tank. See here. The unreacted nitrogen and hydrogen, together with the ammonia, pass into a cooling tank. The cooling tank liquefies the ammonia, which can be removed into pressurized storage vessels. The unreacted hydrogen and nitrogen gases are recycled back by being fed back through the pipes to pass through the iron beds again. So it goes to the cooling tank, the ammonia is stored, and then this material goes back up again, and the process repeats all over again. Now, what the establishment doesn't understand, and I'm sure Evo and Baz and basically anybody that's seen these videos understands, the stars do this naturally. And here's how it happens. The hydrogen and nitrogen are freely available in the thick atmosphere and are observed. They're in there. We can observe them through through spectroscopy. The gravitational field acts as the compressor, compressing material to enormous pressures, provides pressures at all ranges required for chemical synthesis. So the atmospheric pressure itself is far above 200 atmospheres in many respects, but 200 atmospheres is sort of kind of on the surface of the star, so it's kind of a bit higher. Once you get lower, it gets much higher pressures. Incoming meteorites that have iron and the iron collected in the mantle core act as catalysts. They are hot and it can heat up to enormous pressures due to entry. So to get the heat required to form the ammonia, combining the nitrogen with the hydrogen, the asteroid or meteor comes in, burns into the atmosphere as it enters. It creates a tremendous amount of heat, and that heat and pressure combined together can combine that nitrogen and that hydrogen together into ammonia. So lots of materials coming into those objects making ammonia. And just to give you a little bit of a scale of the amount of material coming in, it's been measured that Earth has around 40,000 tons of material entering into its atmosphere every single, I think it's a year, from outer space. So that's not all pure iron, but there's a lot of iron in there. And just scale up the surface area of the Earth to the surface area of Jupiter, Saturn, Neptune, and Uranus, and you get a lot of surface area there, plus their larger gravitational fields, so they can collect more material. They can pull in more interstellar dust and iron from its environment and create that ammonia through a naturally occurring Haber process. Ammonia is synthesized and in its gaseous form can rise up to the atmosphere to cool before sinking again, forming large clouds. So that would be an ammonia rain cycle. So it rains ammonia inside the interiors of those objects, for certain. The leftover hydrogen and nitrogen cycle through and combine, break apart again to find a good chemical equilibrium as more hydrogen than nitrogen is escaping back into interstellar space. So as this process continues and that nitrogen combines and steals the hydrogen, that hydrogen that doesn't combine continues to escape back into space. So the amount of ammonia does build up versus the amount of just hydrogen gas alone. And here's where it gets interesting, Evo. The ammonia provides for the first nitrates for the beginning of life formation because the nitrogen can be used effectively, not having the triple bonds in its diatomic state. This, combined with the production of water on large scales from the oxygen combining with the hydrogen, means young water worlds will have large ammonia clouds alongside water vapor clouds, just at different levels in the atmosphere. And number 7, final, last but not least. This means if you want to find water worlds, look for large amounts of ammonia in the atmospheres of late-stage stars between Neptune and Earth-sized. The water will be hidden. As well, no ammonia will be found in the atmospheres of dead stars, even though they are Earth-sized, as there is no cycle for it to occur with. So when the astronomers are looking for water worlds, they should be looking for ammonia, even though that isn't technically water. But as the star evolves, it forms lots of ammonia alongside the formation of lots of water. So you have both going hand in hand. And also another thing, ammonia is used in cleaning materials. So not only does it provide for the nitrates in the atmosphere of the star, ammonia can also act as a molecule that can break apart large complex molecules to reform back into different shapes and configurations. So think about bone growth. You have cells that break down bone material, and you have cells that build bones back up. So you have both the breakdown and the build up of bone matter inside of somebody's body. You have different cells that do different processes. So the ammonia can act as both something that builds up the nitrates, different types of molecules, and it can also break down others. So it has a dual purpose inside of the star's atmosphere as it forms the beginning of life for the first nitrates. And that's pretty cool to look at molecules as being like that, both breaking apart and building back up again. We know there are some people that do that to us as well. They build us up and they break us down at the same time. Anyways, I think that sums up this paper. I just wanted to share it. Hopefully, astronomers they realize what's going on. Hopefully, in the next few years. Otherwise, it's getting pretty pathetic. All right, later.